Can you
Yep,
start?
I started.
And stage is yours, Joseph.
Thank you very much. Thank you very much for the invitation. It's really a pleasure to be here. And I also apologize a little bit. I'm not in the best form. I tested positive last week. I'm much better now, but it's still not the best shape. But I'll try my best to answer your question. My understanding is that the time format is quite short, at most half an hour. Is that correct?
Yes.
Yeah, so the talk is fairly high level. I have some details, but not maybe as much. So if you have any questions, there'll be an understanding discussion at the end. Feel free to ask. I'm happy to follow up also with you. So what I'm going to talk about, and I will really start quite broadly, just introducing the domain, the objective, the goal.
Moi, je vois les transparents, mais Joseph, we see you, but we don't see your slide on the.
So I'm sharing screen, but I will try to share again.
Oh, maybe we should try.
I'm sharing my screen, so I don't know how to. You need to on your.
Can you see it here?
It's almost good. I see all the slides. I'm very happy, but oh.
Yeah, we were seeing something.
Do you see my screen?
We see you.
Oh, not in
We
the
can
screen,
actually.
but maybe it is.
Sorry, we can actually see the screen from Zoom, and maybe it's an option from your side.
Yes,
Yes, it is.
Look. Is anyone? Do you know how to? I think we should do something with controller.
Oh.
I don't know actually.
Yeah, I mean, in the Zoom, I see your room, I see others, I see myself, and I'm sharing screen, but I don't know how I can make use to see my screen.
No, maybe I can share my, no. I can share my screen, maybe we can. No.
I see someone else's screen now.
Okay. I was trying mine, but no.
Non, moi je contrôle rien du tout. Moi je sais pas.
Can you try it? Sorry.
I'm again sharing my screen.
Okay. Maybe we can share our screen there, but. Was it?
Okay, it's all good.
Okay.
So we see you at the back of the room, and we see your slide in the front of the room. That's okay. That's okay. Thank you, Joseph.
Okay,
Thank you.
So can I continue?
Yeah, absolutely.
Yeah, so if you have any questions, don't hesitate to ask, even interrupt if you want. Most important is that you understand. So, so the problem which we are working on is, the domain is computer vision. So our human visual brain is very good at this. So we can understand and interpret as humans this image like this and understand, recognize the individual entities in the image, like the people, what they are doing, but also we can interpret what has happened in the scene, and even probably can imagine what would happen if we climb the stairs here on the left. Now, achieving a similar level of cognitive competence in a machine is still very hard. So you can imagine really the computer, what it sees is a matrix of numbers, and we want to analyze this input and extract information from this input. And what's exciting is that there is really a lots of visual data around us, from aircraft visual information to cameras around us. And what I'm excited about is what if we could actually learn from all this visual data. And specifically the application which I'm excited now is what if we could imagine, what if we could automatically learn from a sequence of manipulation actions from, say, YouTube videos, from how people do things, and then maybe execute them on a robot, like in an environment where a human cannot do, or actually give instructions to a human to complete a certain task, maybe which they don't know how to do. And so this is kind of what I will focus on in this talk. But I will structure the talk around these three questions, which I believe are one of the sort of important ones in this area. And the first one is how to even formulate a learning problem. So initially, a while back, people tried to solve the recognition problem by writing rules how the object looks like. This, as you probably know, hasn't really panned out very well because it's very difficult to explicitly describe an appearance of an object. Like, how would you define an appearance of a chair, for example? Instead, what really has been the successful approach is actually use statistical machine learning and learn a representation from data of an object. And we need three ingredients for this. First, we need the training data, which is on the top here, which is some positive examples of chairs and some negative examples which don't contain the chairs. Then we need some image classifier here, F, which takes an input image and produces some score, +1 if there is a chair and -1 if there isn't a chair. And then we need some training procedure which will adjust the parameters of the classifier, say, to minimize the number of training errors on the number of training data. And we can actually put some notation on this. We have training data X, Y, Y, Y. The F is the classifier, and typically we try to minimize the number of errors on training data, where L is the loss on individual, which measures the discrepancy between the prediction and the ground truth Y. Prediction F on the input XI. It's summed over the entire training data set and examples, and we want to minimize that over some space of functions classifiers F. Typically, we also have regularization, but I will not talk about this in this talk. So these are the three ingredients. In practice, we typically require millions of annotated training examples. We have classifiers as millions, now even billions of parameters. And we need powerful training hardware, and some of the largest models are trained on certainly supercomputers these days. You may already see what some of the problems are, and the one which I really want to focus on today is the training data. The problem is that even if we have all the sort of manpower to annotate, so first of all, we need a lot of it. So this is an example on the left where someone has annotated all these chairs in, this is still a Pascal image in the image, on the slide. So, but even if you have all the manual manpower to annotate, it's not that easy to do the task because it's often ambiguous. So what is this on this image? Is a table, dining table, desk, or bench. So if you want to, if you have the power, you can't really do it. And this problem is even amplified if you start looking at videos. Like, what is the set of manipulation actions to do with a particular tool, or what is the set of human behaviors that collide with pedestrian accidents? So really now where the community is at the moment is that there is a lot of very good work in trying to bypass and by the way, so what I've just described, this is the paradigm of supervised learning, which has been very successful from annotated training data. And is powering a lot of the successful applications. But there are limits, which I've just described. And what we really want to learn is without the human supervision. There's been a lot of work in that area, and I sort of broadly structured it here into three domains. First one is unsupervised learning. Like really you want to, some often people call it self-supervised, that you just train from the images themselves. And actually you can do things just with images with not annotations, which is exciting. Then there's an area here, it's called weakly supervised learning, where you would like to learn from all available metadata, which includes video, text, speech, audio. You can imagine like a kid browsing the internet and learning from this. And this is the setup where I have done most of my work, and I will show some examples in this. sometimes it's these days called multimodal because multiple modalities, and self-supervised learning. And there is also learning by interaction, as you said at the bottom, when you interact with the environment. I will not talk much about this, at the end a little bit. Yeah, so this is what cross-modal self-supervised learning, and this is what I will focus on now. And the particular example or case study which I would like to show you is learning from narrated instructional videos. So this is quite exciting. So these are videos where people actually show how to do a particular task, like change a car tire, and talk about it. So they would take the individual tools and show you how to do it and narrate it. So it's really a very nice source of visual and linguistic data. And it's goal-oriented, so they show you typically how to complete the task. But what's exciting is, so this is an example of changing car tire. If you get stranded without, you can Google this, but you can do 4 different videos if you don't like the particular one. And in fact, there are really millions of those videos online for different domains like car repair, cooking, gardening, or healthcare. So really, large amount of training data, and it's why it's a very nice test bed to test some of these ideas for which I will show you. And the particular formulation of the problem, which we will, so what we would like to do in this is really be able to extract automatically from this data some kind of an instructional manual, which we can then maybe upload to a robot, which we can do the task or use it to guide a novice. And the particular formulation of the problem, and I don't have much time to really go into detail, but what to notice is that now we don't have, Y is not like a manual annotated labels. Y is metadata here. So we have X still the input and the images or videos, Y is metadata. And now the metadata is not directly in the loss function, but it's entering the problem as constraints. And we are learning some latent representation Z. And so, but the metadata can help the constraints. The question is how we formulate these constraints. And here the latent representation is discrete, and these are linear constraints for very simple thing. But if you can still already with linear constraints, you can formulate, for example, to say that you would like to have a particular action appearing within a certain range of like few seconds or a minute where it's mentioned in the video, by having it summing, like I want sum of latent variables to be sort of corresponding to these metadata annotations. Yet, so and we've done work in this, but I want to talk about that. Instead, you can also expand that formulation, have Z, the latent representation, to be continuous, and actually have the if you wish, constraints to be learned. Really, it's like a learn embedding. So now, if you put it in back in the loss, we are now looking at this learning embedding problem, which probably have seen, and it's been in language for a while. We've been also working on this in vision and video and language. And recently, it's been very successful. You may have seen models like the OpenAI Clip, which are doing something like this on a very large scale on still images. Here we are focusing on video and also trying to push the scale as much as possible. And so here the XI is the video, YI is the caption, is the narration. And so we would like to learn a representation of the video, a representation of the language, so that the two representations in the embedding space are close if they are coming from the same video, and far if they are coming from other videos. So it's fairly simple setup, yet if you put it on scale, it does interesting things, which I'll show you now. The first of all is how to get the scale. So we've created a data set of instructional videos, which is one of the largest available video language data sets at the moment. The question is, how do you get those videos? So we turn to WikiHow, which is a web page where you can Google almost or find almost how to do anything, from how to fall in love to how to make crayon candles or make a mojito. And we took the tasks which are visual, which are sort of not talking about abstract things, how to fall in love, but more are about concretely completed things. So that was the only kind of manual input. And then we took about 23,000 tasks which were in that form, and then collected for those on YouTube videos, which are so more than 1 million videos. So there could be anything, maybe up to 5-10 minutes longer. People are talking about how to complete things. And then chopped those long videos to short 5-10 second clips automatically. And we have more than 100 million clips of this Skype. So in each clip describes a short video and a short narration where the person is talking presumably about what they're doing. Of course, it's not perfect annotation. It may be noisy. Sometimes they talk about their friends. But in our sort of manual study, about 50% of the annotations are reasonable, or at least have some relation to the video content. And really, this data set is the largest currently available video length. Well, there are, from instructional videos, there recently have been also very recently some on a similar scale. But you can see that, these were the data sets which are, many of them manually annotated, but they are in the order of 10,000, 100,000 annotation. And we have something which is now 3 orders of magnitudes bigger, but noisy. But we can run this learning, and this is an example. I will skip some of the details, but this is an example of output. Now we have a little video language embedding space. We can type a query. People call it these days a zero-shot setup. So we type a query and then find videos which are similar for that language query. And here are some examples. So if you type glue, you get videos where people glue stuff. If you type glue wood, you get videos where people are gluing pieces of wood together. Now, if you type glue cut wood, you get videos where people are cutting. So you can see that by composing these words, you can formulate fairly complex queries. Cutting paper is an example here. You get videos of cutting paper. And if you put cut paper in circle, you actually get videos where people are cutting paper in circle. So the key thing here that we are not limited to a fixed label space, but by composing these queries, we actually can search for almost unlimited label space by the compositionality of natural language. And the other interesting thing is the scale of this. So on x-axis, we have the number of training videos, and on the y-axis is the performance, higher, better, on some, and I'm skipping details, video language task. I think it's a video language query. So given a query, how accurately you retrieve on different data sets. So you can see it improves as you train on more data. And this improvement is consistent across several different data sets shown in different colors here. But what's interesting is that on the light blue, this horizontal line is a performance on that light blue data set, which is UCOOK2, on if you actually train a model for this task on the manually provided data in that data set. So I think this is an order of tens of thousands of annotations, which people collected manually describing the content of the videos. And you can see that here in our case, as long as when we start having enough data, we are actually outperforming with this weekly supervised method without requiring any manual annotation. We can get better performance. So really, I've been working on this sort of weekly or supervised methods for a long time. And now we are at this place where finally we are getting better results than fully supervised methods on the data. Of course, the scale is different. We need about, you can see, an order of magnitude more annotations, which are noisy, but we can outperform, but automatically collect and outperform the original method. So this is all online. We have even demos running of this. You can query yourself, including the code. It's a sequence of papers. I've described some of the highlight results, but there is sort of more on this on the web. The second question is really generalization. And here I will also go quickly, but the problem is, how do you have a representation which can generalize across different imaging conditions, like different viewpoint here, or across the intra-class variation? We can really, people perform the actions here, and this is unscrewing the bolts on the tire in very different ways, by foot or by hand. So really, the more formally, the question is, what is the appropriate form of that mapping FX? What is, say, the neural network architecture, or should it be a neural network to really capture the image variation and can be learned from few training examples? And really, neural networks are the choice for last some years, and this is changing from convolutional. Now it's transformers which are doing best, and they have different requirements on training. But of course, what is the right architecture is a question. Like, maybe with this, and for example, this is not going to details. This is practically important in autonomous driving. You want to generalize across imaging conditions. Like if it's day, you still want the car to work, even if it's rainy, even if it's the beginning of the day, or even if it's in the night. And we have a whole sort of line of work in this. There is a website, the benchmark this is for localization. And another line of work is for how to represent 3D. So one of the open questions in this representation. We have worked on estimated poses of objects, estimating poses. So given an input one or more images to get unknown objects, in this case, get their accurate poses in order, often this is for robotics, to be manipulated by a robot. And if you are working in this area, this method actually works very well. We won a competition with it. It's publicly available. You can use it and try it out. But where I want to spend a bit more time now is on the third question before having questions from you, and this is really the reasoning about data. And of course, what does it mean to reason about visual data? And this is still, I think, very much an open problem. If you Google it up, you find a visual reasoning website where there's a data set, and so people are working on this problem, of course, from different directions. In this data set, the goal is to recognize relations. So reasoning would be recognizing entities and the relations between them. So and being able to answer questions like, is the ball to the right of the green apple, for example, given an image like this? And the relations could be spatial, on top of, behind, and to the left, or it can be attributes like, is it green or is it soft, for example. And so we've been working on recognizing relations among entities for quite some time, and it's a hard problem. I don't think it's solved at all at the moment. Here are some examples of recognizing unusual relations, like car under elephant or person riding a horse. We were also looking at this in videos, where of course, the data is an issue here, but one can use temporal continuity, but there are also actions like slicing apple or washing a bike. And one can also actually localize these relations in the video. The problem I want to focus a little bit more is a video question answering. Here, so here are two examples. These are still frames from videos. This is actually a video. And the question is so that for you to understand what the problem is. So this is the task. Given a video, here you see one frame, answer a question, what type of material is the man touching? And here the question is, given the video, what animal is shown as a cutout? And the algorithm needs to automatically answer these questions. So here are some examples. The ground truth, as you know, as you recognize yourself, is wood. But here are some baseline algorithm answers, and this is an example of our algorithm which we've just developed, which can answer correct. And so you can see that in order to answer this, you really need to understand what is happening in video. There is some relation. There is a person touching. There is the wood in the image. In this case, again, you need to understand a bit, like recognize what's happening. So it is a hard problem. And the reason I want to mention this work is that the approach which we took is, again, a slightly different one. So rather than trying to explicitly localize the entities of the object, like the objects in the video, and recognize the relations, like what type of material is this object made from, we have an architecture and throw lots of data and try to learn this kind of reasoning capability to answer the questions implicitly from the data, not explicit representations, but more implicitly. But the problem with this is, how do you get a large amounts of data for this task? Because for this task, you need to have a video, a triplet, video, a question, and an answer. So that's the ground truth triplet for this task. But there are no data sets with such a large number of these triplets. So what we did, we turned to our data set, which you saw with the instructional videos, which have videos and a narration, like there is someone talking, cut the white felt in circle, but no questions and answers. But there are data sets like that with questions and answers in language only, no video. So we took those. And so you can actually learn a model which will take a just language question, so language sentence, and generate a question and answer, possible question and answer from that. And then, so using this algorithm, we can actually automatically generate a large number of these video question answer triplets, and then learn a large transformer architecture, which using a contrastive loss, we can train on these large amounts of data to answer these questions. So it's relatively simple architecture, but the key idea is here that we automatically learn these triplets. And here is an architecture to do this. So we have videos and then the aligned narrations. And then we have several components. There's a sentence extractor, which does punctuation, then it's question generator, an answer instructor, which together they, given this sort of unstructured input, can generate a short clip with question and answer triplet. Of course, it's not perfect. They are again noisy, but we can still learn from that. And again, the data set is very large compared to existing video question answering data sets, going from thousands to really millions of examples. And here are some example results of this. Doing this sort of outperforms existing results on existing data sets. And here are some examples of the results. So here, what is in the blue plate? And the answer is butter by the, or what is the man cutting is an example, and the answer is pipe. There may be, I think, one more example is in here shown. What is being made? The answer is snowman. Of course, the problem is not solved. There are still sort of things to do, but this is to show that with this large amount of data and now still simple architecture, one can sort of learn to address this task. Now, in the last few minutes, I want to also say that, in fact, here we've talked about relations between objects in the image, maybe answering questions about the objects. But in fact, the relations are dynamic and in 3D. And this is an example of, and this may start being important once you want to actually put the camera on the robot and start interacting with the world, because it's not, just being able to put boxes in images may not be sufficient. So here is an example of our recent work where we given an input video from YouTube. This is again someone sort of showing how to use a sledgehammer. We can extract a motion interpretation of the video. So this is the motion of the person, motion of the tool, together with the contact forces, which are shown in yellow here. So actually we can estimate the 3D motion of the person and the tool, the contact interaction between the person and the tool, and estimate the forces and moments. The moments are shown in white. So this is, and in the formulation, this is really, one can, at the moment, we don't use it in learning. We just use it to correct or do better inference using pre-trained models. But you could imagine also doing learning and putting physical and geometric constraints in the learning problem. And here we can also apply this technique. So we have given input video, we'd like to transfer the skill onto a real robot. And in order to do this, we actually consider are here in the form of a simulator. So we can align the video with the simulation and then run a reinforcement learning together with some optimization to actually learn a policy which would then execute the task in the real environment. With this, I will finish. I think it's a very exciting area to be in at the moment, where we will see in short term interesting applications sort of being executed. But long term, I think we still are quite far, and we'll see, I think, lots of interesting research in autonomous sort of learning, reasoning, and interaction, and combining different fields like computer vision, machine learning, robotics. And with this, thank you very much for your attention, and I'm happy to answer any questions you might have.
Thanks a lot. Thank you so much. Is there any questions from our side or from Zoom?
Okay.
May I?
Sure, Yanis.
So, Josef, thank you very much for your talk, and congratulations on this excellent work. And thank you for providing us with this great data set where we can learn many things. I have two questions. One is about the data set, how to 100 million. If someone wants to use it to learn, for example, a video encoder from scratch, it is very computationally intensive. So it's like beyond the capabilities of many groups. So do you have any insights on how this could be handled at a smaller scale, like what would be a subset of the data set that could maybe become standard, and some teams could, you know, test the performance of different encoders, you know, at a smaller scale?
Yeah, so this is an interesting question for, thank you very much. It's of course, the scale and the compute is a problem. I think in France, it's because of the Jonzai supercomputer, or Jonzai cluster, actually one can do quite a lot of things. So it's not yet, I agree that, you know, trainings, you know, something like this on the scale Google does it, may be possible on Jonzai, but would be very expensive. So I think from that perspective, maybe better to do it like a coordinated effort between many groups rather than just like every group trying to do their own thing. There's been a great example of, I don't know if you heard about the Big Science project, which was driven by several French groups, but also Hugging Face, who is a company in natural language processing, who actually are, I think at the moment, training on Jonzai, publicly available, multilingual language only, like a model. So I think it is, and I think in Europe in general, we are relatively sort of well positioned with these. I think Jonzai is a great example to actually be able to reproduce some of these results, which are often done in Googles and Facebooks. Yet, I agree with you that, you know, a lot of the, you know, it's difficult to do it on that scale. And I think on this, in this work, for example, we often use like you can do quite a lot with already pre-trained components, which we only fine tune or build on top of this. So I think here we use a pre-trained language model here at this, which we sort of put additional layers, which we adapt to this. And similar for video, I think here we are using one of the pre-trained models, which we did, you know, before in that space. So I think probably it won't be possible to train a new model for every CVPR paper, like really the basic representations. There'll be few of those, but one can do interesting things with those existing ones already. Does it answer your question? Like this model has not been trained from scratch. It uses existing components and puts them together in this architecture and sort of fine tunes it for the task, if you wish.
Well, partially, yes. I mean, for sure, we can use pre-trained models or components, but the question was more like, if it happens that your work is on the pre-training part, and so, for example, you want to modify the architecture, and then you need to show how it works when you train it from scratch. At this point, you cannot use a pre-trained component, and so you really need this training. if it would be possible to have a smaller subset that works, somehow decently on smaller data, that this would be desirable. But it's not like someone will do on their own. It would be nice to have like a more standardized.
Sure. Of course, I think here the more collaboration, the better. I think in this, I think the big science project, I find it quite nice and inspirational, and hopefully we'll also see something like along these lines also in more in the visual domain. And in our case, just to give in the how to 100 million case, so we collected a data set, and in the data set paper we actually found that you can't quite train it in Inria Willow cluster. So and we did sort of two things. We applied to Jose, but Jose just started, so somehow they rejected our application. Maybe it was too big, or it was. I think it was just beginning to open. So and in the end, we went with the route that our student Antoine Miege went to DeepMind for an internship, and there he actually trained those big models on this data. But when he came back, he actually re-implemented this also, and all the code is publicly available. But he didn't retrain on Jose because it'd be too expensive. So I think we have the code to do it. He created the code, but he didn't do the training because he couldn't justify just training it on the public resource. We already had the model.
Right. So thanks a lot. So the second question is about. When I saw your retrieval application, this cross-model retrieval, I thought of your work on bag of words and video Google, which was like 20 years ago. It must have been quite a journey. So how does it feel to have such results today at this scale and being able to do this kind of queries?
Yeah, no, I think it is interesting. I would still say that I think already these results could be potentially useful for some things, yet I think the problem is still far from completely being solved because we can't quite localize these things, and also the compositional. I think with this scale, it's really getting better. Like if you look at the OpenAI clip model results, they are really, quite nice. Of course, for example, the model does not localize very well as well. So I think that there are still things to do. And what's interesting is that to make that demo, there is a demo online. We actually had to go, because on that scale, you have to use efficient indexing techniques. So we did use like, vector quantization and product quantizations to actually make an online demo to index on the embedding vectors. So I think on that work on efficiency, of course, is still very relevant because if you want to make it work, you can't do nearest neighbor search exhaustively.
Of course. So thank you very much again.
Other questions here?
Can you go back to the slide where we see a robot mimicking a human?
Oh, yes. Here we. Can you see it?
Yeah, I mean, although the robot is mimicking the human, it is doing a pretty bad job.
You mean that it's losing some of the material on the side?
Yeah, exactly.
Yeah. So I think it's
so it didn't get the purpose of the
So the difficult part of this is really get the dynamics of the, imitate the dynamics of the motion. So and at the moment the execution is in open loop. So the robot itself at the moment, he doesn't have an eye. He takes the simulation and he learns to do the motion in the simulation. The next big thing really is to add visual feedback and really start with controllers which would be able to adjust it on the real robot and adjust it on a do like a feedback-based policies in the real robot. So I think that's like one of the big things going forward, which we also are looking at. But it's a great point. I think there is a lot of work which still needs to be done here. And I will maybe finish on this. So I'm not a robotics expert. So I think we work on these robotics tasks with roboticists. But for me, what was very interesting coming to this area is that it's not easy to program the robot in the sense that, just doing like a motion like this, it is not easy. So I think there is really a place for being able to learn from these videos how to do this. I think there are maybe two things which I think are important. So to make this happen, we actually don't look at the human at all. We really look at the motion of the tool. So we imitate the motion of the tool. So there is no, so it can be any morphology. I don't have these results probably here, but we can do it on a humanoid robot, on this robot in different degrees of freedom because we look at the motion of the tool. But recovering the motion of the tool requires modeling the human because otherwise it's very difficult to get that tool of the video in 3D automatically. So I think there is a space of really learning from these videos on a large scale to just get the variety of motions and interactions from the video. And I think the second space where I think there's really a lot of potential in this area for learning from, say, instructional videos for robotics is reward functions. And this is kind of what's happening here already a bit, but I think it's very specific from this single video. But I think a lot of the current work requires really manual engineering. And this was also a surprise for me, how much kind of effort goes into tweaking the reward functions to get these, in prior methods, when you see the results, often this is a result of a lot of tweaking the reward before even you can start running the reinforcement learning. So if we could automatically learn reward functions from videos in order to learn how to do or complete this task for a variety, so that we don't have to tweak it for every single new task we want to address, I think that would be a big thing as well.
Is there any other questions? Then it's okay. Thank you so much, Josef SIVIC.
Thank you.
Thank you very much for the invitation.
Thank you very much. Thank you for all the many people that were around, and see you soon at the next Link Media Speak Science. Bye bye.
Bye.
Bye. Ciao.